Today, we're moving into what will be, I think, the last of the topics that we are going to see in this class. And that's going to be PageRank, which is essentially the algorithm that Google is using to rank pages and provide search capacities. And but to sort of explain this topic better, we're going to look at some of the underlying ideas which have to do with what are called Markov chains. And a Markov chain is a class of what we call stochastic processes. So I'll be going over this. I am still stuck at home, having issues. Well, I mean, problem is those short lectures, going to the university just to tape a short lecture like this is not really working. So I'm staying at home for this one. I have added a thing that I can write on. So if I need to do examples, I'll be able to do that using my tablet. So, PageRank and Markov chains. Let's start with PageRank, but we'll probably today's lecture and a bit of next lecture probably as well are going to be about Markov chains themselves, and then we'll come back to PageRank. But first, I'll set the stage by saying, okay, what makes an important web page? Essentially, that's what PageRank is trying to answer. So I'll just explain the genesis of this, because for most of you, web is something that has always been. I'll point out that I'm a little older, of course, and I saw the birth of Google. A lot of you probably were either not born or very young when this happened, but in 98, we saw the first start of Google. So before that, we used to, I mean, one of the most well-known search engines is something that was called Alta Vista, which I believe has died long since. But first there was Alta Vista, and then a few other search engines, and then Google came on the market, and they actually were much better. And one of the reasons they were much better is that their algorithm provided much better search results. And that's what we're going to look at. So in terms of what it does, the PageRank algorithm, it gives each page a rating of importance. And this is something that's going to be recursively defined, where a page is important if there are other pages linking to it. So the importance of a page refers to the importance of the pages that refer to it. So if your site is linked or your page is linked by other pages that are considered important, then your ranking is increasing. Okay. And in practice, you'd like to rank all the pages in the web like this. Of course, now it's become a very fastidious enterprise, but it is something that is feasible. And the overall idea rests on something that Page and the other authors of the paper that Google is based on is what they call the random surfer model. Surfer, not a guy on the waves, a web surfer. Okay, and the idea is that if you put somebody on the internet and they're let free to roam the internet essentially, and they follow some links from page to page, then the probability, the page rank essentially, is going to be the probability that your random web surfer lands on a particular page. And and the higher the rank of a page, so the more popular a page, the higher the probability that whoops, I don't want to look at the keyboard settings. The higher the probability that you end up there. Okay. And the reason why we're going to talk about Markov chains is that this idea of a random surfer is something that is essentially using a Markov chain. Okay. Yes, just a remark in passing, you can see this P here written like this with a double bar. Why? Okay, I'm using something which is correcting my, this is going to be annoying. I will take a detour. Okay, before I continue, so that P that I'm trying to write and that the software is correcting, and that you see there on the page, means probability. Okay, and I'm going to be using this often. So I'm back, and now I'm under Linux because apparently I wasn't managing to do anything with the software I was trying to use on the Windows, and OneNote is bad. So what I was saying is this symbol here, which of course I'm having trouble selecting because there has to be some issues. This P capital like this is probability, and I'll be using it from time to time. So back to PageRank and what it is. So a random surfer model, and that is an example of a Markov chain. So this is where we were. So as I said, we are going to start with a little foray into Markov chains to explain later what the random surfer model actually is. So a Markov chain is what is called a stochastic process. So a stochastic process is a dynamical process where something that is called typically the state of the system, and that would be true also for models for what are called deterministic system, but a stochastic type of process is something where the state of the system evolved through time, governed by stochastic rules. And so stochastic means random. Okay. So a stochastic process is something where the state of is random through time. And I mean, there's plenty of examples. Most processes are stochastic, but sometimes we can approximate them using what are called deterministic methods. So if you have ever seen ordinary differential equations, this is a deterministic model. Okay. What's important with Markov chains is that they are what we call memoryless, and I'll come back to that. But what that means is that their evolution through time, the change at a given instant in time only depends on the current state of the system. It doesn't matter what the system has done in the past. It just matters where it is now to determine where it's going to go in the next instant. And one thing that makes these Markov chains very appropriate for this course is that they are a perfect example of a combination of matrix analysis, matrix theory, which we saw in the first part of this course, and graph theory, which has occupied us for the second part of this course. And you'll see that really they combine both in a very elegant way. And they have applications in data science. So not necessarily per se as Markov chains, although you will see them used from place to place, but more as the theoretical underpinning to things such as hidden Markov processes or Markov chain Monte Carlo methods. These are things that are used in machine learning, for instance, and so these are important objects to understand. And I'll point out that I think this is a very nice way to finish this course. I mean, we'll be essentially looking at this for the remaining 3 or 4 lectures, because they're also quite pleasant, quite easy to understand, and interesting to manipulate. I mean, my experience is we had a course on math modeling in 2nd year. Now it's gone to 3rd year. But when it was in 2nd year, I used to teach Markov chains, and that was one of the favorite parts of the course for most students. It was the part that they really got a good understanding of. Sorry, sometimes you'll see my mouse moving. It's simply that I have, otherwise my screen shuts off. Although the video doesn't shut off, I don't see anything anymore. Okay, so Markov chains. So let's now switch gears for a while and look at Markov chains. I have to be mindful of the time. So what's going to happen in a Markov chain? The idea is that you're going to conduct an experiment, and that experiment is going to have a set SR of possible outcomes. And these outcomes can be, let me see if I can manage to, okay, I should define things here. And let me point out the outcomes are going to be, typically we represent them like this, because S1, S2, this is proving to be a little messy, SR. So what you can see is that I'm drawing them as states, as vertices, and indeed what's going to happen is that you're going to have a possibility of transition between states. Okay, the outcomes are what we call the states. And these outcomes can be a bit of anything. Okay, so simplest thing that we could, one thing that you could think of is I have a light bulb, and that light bulb is either on, not on, is either still working or not working. And so the states could be working, not working. It can be much more complicated than this. Okay, so I'll have a running example that I'll use throughout the course, but I haven't come to that yet. So we have this experiment. It's got a possible set of outcomes S1 to SR, and I'm repeating this experiment n times, and this n can be large, typically is large, potentially infinite. Okay, so, and this is a luxury we have mathematically, is we can think of repeating something infinitely many times. It is not a problem for us to think in these ways. Of course, for us as human beings, doing so is not necessarily easy, but mathematically it's easy to think about things that way. As I said, the system has no memory, so where it goes next only depends on where it is now. And what we say is that there is a probability that a certain state, Sj, or a certain outcome Sj occurs the next step. Okay, we're going to think about things as happening in steps. You can think of them like an easy way to remember this. A step can be, for example, one day. One day, my system is in state Si. The next day, it's on state Sj. Okay, there's a discrete aspect to the way the system moves from one state to another. So the probability that Sj as an outcome happens on the next step, given that Si occurred on the previous step, is given by this value Pij that we have here, which is simply the probability that we get Sj given, this is a probabilistic notation, those of you who've taken stats know this, given Si. Okay, so this is the probability that I was in Si and my next step, my next outcome is Sj. Now, we are going to have to assume that we are forced to go somewhere. Okay, so if I'm in Si, my next outcome has to be one of the possible outcomes. Okay, I have to remain in one of the possible states of the system. So if you go back to my light bulb example, if a light bulb is not broken at a given instant in time, the only possibilities for it at the next instant in time is to be not broken still or broken. It can't be, we don't know. Okay, it has to be one of those two. So when you're in a given state, you have to go to another of the admissible states. So that means that the sum of those Pij's for a given I is 1. Okay? So I can only go, I need to go somewhere, and I can only go to one of the allowable locations. And so that means that we have that the sum on J of the Pij is equal to 1. And just in passing, so you'll see this is going to connect back to something we've already seen, which was stochastic matrices. Okay, so here I'm thinking of the possible transitions as being stochastic, as being a random variable, okay? Because I want all of them to, actually not a random variable, I want them to be a distribution of probability. I want the sum to be 1. Of course, sum may be 0. If you look at my graph here that I have, my probability of transition here from S2 to S1 is 0. But altogether, I have to have something that sums to 1. Actually, so that means that, no, that one could be okay. Okay, I don't need to edit it. So how do we define a Markov chain in practice? Well, suppose we have an experiment with a finite number of possible outcomes. So this is important. We're not considering an infinite number of possible outcomes, just a finite number. The sequence of outcomes we get is a Markov chain if there's a set Pij that is of numbers, okay? So there's going to be r squared of them because we have r possible states, possible outcomes. So we have a set of numbers such that the probability of outcome Sj given Si in the previous experiment is given by this Pij. Okay, so Pij is the probability, which I should have written with my the P that I was mentioning before, but never mind. I will edit the notes. It's the probability of getting Sj on experiment n plus 1 given Si on experiment N. And the outcomes are the states. The PIJs are what we call the transition probabilities. And the matrix that we get from those PIJs, so there's R rows and R columns in there, this matrix is the transition matrix. And I'll point out, that's an important remark here, that this is going, so the way I explain this here, we would be looking at essentially the transpose of everything we've done so far, which is a little silly sometimes, but never mind, okay? So bear this in mind. So Pij is going from I to j, which is good in terms of graphs. It is very much what we saw for graphs, but you'll see that in terms of matrices, it's going to be a little annoying because we are going to be dealing with row vectors because of that, not column vectors. But that's not really important, okay? But bear that in mind. So that matrix that contains the transition probabilities is a very important matrix, and it turns out we've seen such matrices before. Okay, so I'll just go over its properties a little bit. I need to be mindful of time. So it has non-negative entries. All its entries are less than 1, and the row sums are equal to 1. Okay, so if you recall, this means this is a row stochastic matrix. Okay, and I'm going to come back to the definition here. We've seen it already, but never mind. It's important, so we'll see it again. So we have a matrix which contains in each row the probability of transition from one row into the next, from one state into the possible states. So here I come to my example. And that's going to be our running example throughout this this part of the course on Markov chains. Okay, and it has to do with Mendelian genetics, and I'm going to simplify it to the point where those of you who are in biology, if there's any of you in biology, you'll probably be sort of terrified that I would explain things this way. I mean, it is a super simplified vision of Mendelian genetics. So we're going to say that, okay, you have a phenotypic trait. So phenotype is how a genome, like how the genes that you have expresses itself in terms of the characteristics that, for example, are visible, but not only visible, of course, okay? So that would be, for instance, eye color, hair color, handedness, whichever thing you want to think about. Okay, so and I'm going to think about a very simple phenotypic trait, and I'm going to say, well, that phenotype is determined by having a specific pair of alleles. And for simplicity, I'm going to call these alleles capital G and little g. You can have 3 possible combination of alleles. You can have what is called a dominant combination, which is 2 capital G's. You can have a capital G and a little g, and this is called a hybrid. And we are going to assume, and this is not true in general, okay, but it doesn't matter which order these alleles come in. It's either capital G, little g, or little g, capital G. We consider them to be the same thing. So that's a hybrid. And otherwise, you can have a little g combination, and that's what we typically would call a recessive situation. If you have the same allele twice, you're called a homozygote. and you're a heterozygote if you have a combination of the alleles. Capital G, little g, or little g, capital G. So capital G, so double capital G's or double little g's lead to different phenotypes. Little g, capital G is the same as the little g, double capital G. So that's why you call double capital G dominant. Okay, because if you just have one of little g's going in there, so if you're a hybrid, you're like the dominant, you show the same trait. So say, for example, capital G is being right-handed. That would, again, this is a super simplification, but if capital G is being right-handed, little g is being left-handed, capital G would be also right-handed, but with some left-handedness inside of you. I'm thinking of this because I'm left-handed. Okay, so what happens is that in sexual reproduction, you inherit one allele of your pair of alleles from each of your parents. So your father will give you one allele out of two they have, and your mother will give you another allele out of the two they have. And we're going to assume, and I mean, this is like in simple genetics, that's what happens, that which allele you pick from each of your parents is completely random. So you have to select one allele out of the two of each of your parents, and which you select from each parent is random. So there's some simple situations if you think about this. So if both of your parents are capital G, you're selecting one allele from one and one allele from the other. But if they're both capital G, you can only select a capital G. Therefore, you end up with a capital G, two capital G's. Okay. The same way, if both of your parents are little g's, then you can only select a little g from your mother and a little g from your father. So the only thing you can be is a double G, little g. Now, if you have a parent that's dominant and a parent that's recessive, you have to be hybrid. Okay. And the other cases are going to require us to look at a little bit more detail about what's going to happen. So let's look at what happens. Suppose one parent is dominant, double capital G, and the other is hybrid. So what I've represented here is one of my parents, and it doesn't matter which one is the father or the mother. Okay, in this situation, you're picking at random between the two, and that's it. So I have a double capital G here, so this is a dominant, and I have a hybrid here. So what happens is you pick at random one allele from each of your parents. So what that means is from this parent on the left here, the dominant one, I am going to select either a capital G or a capital G. Okay, so I'm illustrating this by showing which of the alleles I'm picking up. And from the hybrid parent, I'm going to pick either a capital G or a little g. Okay, and I have equal likelihood of picking each one of those. The probability of picking capital G or little g is the same. It's 1/2 in this case. So now when I've selected those here, 30 minutes, okay. When I've selected one of those here, which is simple because they're all capital G's, and I've selected one of those here, that means that my offspring can be one of the four following possibilities? Well, it's going to be a dominant, or I've selected a G here, a capital G here, and a little g here, which makes that offspring a hybrid. Or I've selected a capital G here and a capital G, so again, I'm a dominant. Or I've selected a capital G and a little g, so again, a hybrid. So this is what I illustrate here. If from parent 1, let's say this is parent 1, from parent 1 I've selected, I have no choice, a G or a G, and from parent 2 I've selected a capital G or a little g. And so that's my possible outcomes. And to determine the probability that the offspring is either hybrid or dominant, in this case, I just need to look at the number of possible outcomes, and there's 4. Count how many of the possible outcomes happen. So here I have 2 possible outcomes in the 4. So capital G, or capital G, little g. And so I have 2 out of 4 and 2 out of 4. So the probability that I have a dominant offspring from a hybrid and a dominant parent is 1/2. And the probability that I have a hybrid offspring from the same pairing of parents is also 1/2. Okay. Another more complicated situation, I mean, the most complicated situation that I can get, is that if I have 2 hybrid parents, so if both parents are hybrid, what I'm getting is I have a parent that's hybrid, another parent that's hybrid, and if I go through the possible choices, I can pick a capital G from that parent and a capital G from that parent. Or I can pick a capital G from that parent and a lowercase g, small g, from that parent. Or I can pick a lowercase g here and a uppercase g here, or 2 lowercase g's. And because we've said that those 2 here are equivalent, we can summarize the probabilities in the following way. I'm going to have, you can see, capital G, or lowercase g happen each in 1 out of 4 cases. So they have a probability 1/4. And the hybrid case happens in 2 out of 4, so 1/2 probability of happening. And finally, very similarly to the case of having a hybrid and a dominant, if I have a recessive and a hybrid, then the same way as I had before, I can get, in 2 of the cases, I will get a recessive, and in 2 of the cases, I will get hybrid. So that means that the offspring of a recessive and a hybrid have probability 1/2 of being hybrid and 1/2 of being recessive. Okay? So keep that in mind. Yes, keep that in mind. We'll come back to that very soon. So now let's go back to sort of a general case of the Markov chains. So if I write Pi of n to be the probability that state I occurs on the nth repetition of the experiment. Okay, so I'm looking for, why is this not working? No, this is proving to be, okay, this is working. Go away. Go away. That's, you can do the go away thing. Why? This work? Oh, okay, my other pen works. Sorry. I can erase all these things. So I'm interested in knowing the probability that I will be in state let's say 1, for example, at time n. So this is completely off. I am not yet mastering. This is not the laptop I was using before. I probably should have used that one, but it wasn't charged this morning. So anyway, so I'm interested in that probability. Probability that, for instance, I am in state 1 at step n. Okay. Nth repetition of the experiment is step n. So because I need to be in a state. Okay, remember, this is what I've been emphasizing since the beginning. So here, for instance, what you see here, you have 3 states, and I have to be in one of them. So that means that the probability that I'm in 1 or 2 or 3, etc., up to R, is 1. Okay, remember, so I don't know if you've seen that so much, or in probability theory is plus. And is times. Okay, so what this equation here means is that the probability to be in 1 at step n, the probability to be in 1 or 2 or all the way to R is 1. I have to be in one of those. I cannot not exist. The system assumes that I'm somewhere. And I want to determine the probability that I will be in state I at time n plus 1. Okay, so assume I'm somewhere and I want to know where I'm going next. So what's the probability that I'll be in state I on the nth repetition of the experiment? Well, there's are different ways, potentially, to get there. I can be in state 1 at step n. And then my probability of moving from 1 to I is P of Si given S1. Okay, so this is this number here, P1I, probability of going from 1 to I. But prior to that, I had a probability 1 at step n of being in step 1. Okay, so the probability that I end up in state I at time n plus 1 is this, the product. Remember, so as I just said a moment ago, in probability, if I want and, I multiply, and if I want or, I sum. So this is saying the probability that I'm in state I, given that I was in state 1, is the probability that I make a transition from state 1 to state I, and that I was in state 1 at time n. And I'm going to often say time for step, okay, because this is like, think of, as I was saying before, think of days moving forward or something like this. Okay, so often I'll say time instead of state, instead of step. But that is it. Okay, so I was in step 1 at time n, and I make that transition. The same way, I could have been in state 2 and made a transition. And therefore, the probability of ending up in state I, given that I was in state 2, is P2I times P2 of n. And so on and so forth. I can do that for all states. And the last one is that I was in state R at times n. And I've made my transition into state I. And so this is PRI times PR of n. Ooh, I need to soon finish. Let me just write this up and I'll finish here. So this means that if I'm writing the probability to be in state I at time n plus 1, it is the probability that I was in state 1 and I move to state I, plus, so I was in state 1 and I moved to state I, or I was in state 2 and I moved to state I, or, and so on and so forth. I was in state R and I moved to state I. And from the computation we just did, this means that the probability of being in I at step n plus 1 is P1I P1 of n plus, and so on and so forth, PRI PR of n, which we can write, of course, as a linear system, because, okay, I've done this for I, but I need to do it for I from 1 to R. So the P1 of n plus 1, so the probability to be in state 1 at time n plus 1 is this quantity here. Okay, so it's the transitions into 1, and the probability to be in state all the way to the probability to be in state R at time n plus 1 is this quantity. This means that we can write things in matrix form. And in matrix form, and this is what I was saying earlier, we are going to write this using a row vector. So this is going to be a bit different from what we've done before. And just because I'll be always using row vectors, I'm not going to say the vector is a column and transpose it. I'm going to use the notation vector for something that is a row vector. So in matrix form, what I get is that the state at time n plus 1 is equal to the state at times n times the matrix P, where the state at times n, or n plus 1, it doesn't matter, okay? The P of n is simply the row vector P1 of n, P2 of n, or to PR of n, all the way to PR of n. And that is a probability vector. From what we were saying here, we need each one of those to be a probability vector. So this here, Pn, is a row probability vector. And this matrix Pij is the transition matrix that we evoked earlier.